The last thing we're going to talk about in our adventures with multiple linear regression is looking at two methods to select a model. Before I get into this, I want to show you how we used to select models. So the following data that I have on, well, it's not really following, it's on the left, is from a wine producer who wants to know which chemical compositions will create the bouquet of the wine, the smell. So these are a bunch of Pinot Noirs, which if you don't know your wines, it's a very strong smelling dark red wine. Um, and there's some chemical elements that have been recorded for a bunch of different wines, and they recorded 17 of them. It's listed right here. If you don't know your chemical elements anymore from chemistry, they are listed right below for the worksheet description. And what we want to do is we want to try to predict what the aroma is going to be for a particular wine. So the first thing we're going to try is, hey, let's see which of these is linear and which one are not. Because that is really what you should be doing first in order to determine whether or not a variable should be included in your linear regression in multiple or simple. So we're going to go up to graph and then scatter plot. And we're going to do simple and hit OK. Now, I want to try to predict aroma for literally everybody. So I'm going to do aroma with potassium, aroma with phosphorus. Sorry, that one I had to think about. Aroma with cadmium, aroma with salt, aroma with silicone. This is boring at this point. Oops, I put in aroma twice. You should be doing 17 graphs here, which I should probably pause and write all of these to make sure that I don't miss any of them. Or you could watch me boringly click through all of them. And maybe. Okay, now I'm saying maybe too much. Boring. Almost done. Now for the hard ones, the ones where you have to scroll back and forth. Uh-oh. Oh no, wait, I have 17. I have all of them. Yay! Okay. Whew. All right. I'm not going to worry about anything else, but I'm going to hit OK, and you're going to get assaulted by the number of graphs that are present. Okay, this is disifying. And what we're looking for is anybody who has nonlinear shape. Now, right here, I've got me some CD. Is that cadmium? Woohoo, basic chemistry, I was right. All right, this one looks like it has no shape whatsoever, so I probably should be throwing out cadmium. I'm going to include it just because. Nope. Let's look at a couple others. Here we have, oh, chromium doesn't look like much of anything. Oh, this has got a little bit of a negative pattern to it. Same with aluminum, looks pretty negative. Who else we got? Now, barium looks pretty good. Why did I say down here that it looks curvy? It does have a little bit of a curve to it, so I might consider getting rid of this one. I could see this end up being something that looks nonlinear. What you should be doing is looking for nonlinear shapes and then dropping the variables that look nonlinear. Oh, nickel's so much worse. It looks like it's got outliers. Let's just update my notes. Let's drop nickel. Variables like nickel look to have outliers. And should be dropped. There are other ones in here that might have nonlinear shape. And really, this is just a rule of thumb of how to eliminate a couple. I'm going to just use everybody for fun. This one's terrible. Copper is actually pretty bad. Strontium's pretty good. That one looks weak. This one looks pretty linear. It's got a little bit of a curve to it. Oh, maybe that's why what I meant was, you know, this is probably me doing, but I meant, you know, boron, not barium. Good job, me. Anyway, that one looks good. That one looks weak. That one looks okay. These are all pretty questionable, actually. Anyway, so that's what you should be checking first to see if they have linearity. A bunch of these looked pretty questionable and probably should be removed. I'm going to ignore that for now. and move on with forming my linear regression. So what you should do, or what we used to do back in the days, after we eliminated a few of them, we would go up to and create a regression. So we would just like stat, regression, regression, let's fit ourselves a regression model. And we'd throw in our aroma as our response, and then our continuous predictors. So I'm just going to click and then drag to select all of these, and then hit select, because that will produce everybody in there. And then I'm going to click results and deselect, where is it? The analysis variance, the ANOVA, just because we don't know what an ANOVA is yet, and that is what is in chapter 20, and once we know what it is, it'll be very useful to us. But for now, we're not using those results for anything, so I'm just going to unclick them because it makes my model shorter, because this is going to produce a huge bunch of stuff. And then I'm going to go ahead and hit OK, and then hit OK again. And it's going to produce a bunch of things. So I'm going to make my session window a little bit bigger so we can look at some of those diagnostics. So here's the regression summary for our model. Our S is pretty good. Our R squared adjusted is a little bit left to be desired. It's, it's above 50%, so I'm okay with it. As you look through your values here, I'm hoping you notice some slightly questionable things, like some of these have some really high variation of inflation factors, so these probably are related. So for instance, like whatever MO is, because my brain is failing me, and strontium and lead appear to all be related, so I would be eliminating these three for collinearity. But what I really should be doing before I look for getting rid of collinearity is deciding which of these are insignificant, which of them should not be included in my model. So just below, I copied this and I highlighted some of the ones that have some higher values for their p-value. So in particular, like cadmium, which we saw had a bad shape, magnesium, nickel, and then if you look down here all the way down to potassium, you'll notice potassium has the largest one. So what we would do next is we'd remove potassium from our list of variables and we'd rerun the model. Not kidding. So we're going to go through and one by one try to eliminate 17 different things, and it would take us 17 steps to finish at max. But that would be like eliminating everybody, so probably not that. You can imagine how this can be very time consuming for large data sets, especially if you have a large number of variables to select from. So that method just doesn't seem like all that great of an idea. So I'm going to show you how to do the two other methods that we actually prefer when you have multiple variables and you're trying to decide how to select your variables to include your model. The first one we're going to look at is what's called the backwards elimination stepwise regression. Super long name, but pretty easy to use. So we're going to go up to stat, regression, regression, and then fit regression model. Similarly, we want to have aroma in there and our continuous predictors. But what we want to do is we want to have Minitab decide who it's going to eliminate. So in order to do that, we're going to go ahead and hit this stepwise button. Okay, and then it's right now setting as, oh, well, you don't want any method, so that's cool. We're going to change the method to backwards elimination. And now it's got a list right below of potential terms, and I means that they're going to be included. If there's any of them that you want to include in every single model, you can highlight them and hit this button, E, include every term in every model, to make them be included. So there's one you were really strongly felt like should be a part of the model and should be definitely included, you would do that to force it to be present in all of them. And then the last thing I'm going to do is I'm going to go down to the display options and change this to include details in every step. So normally I leave this set as details about the method because that just produces the final step for me and tells me how it selected that and who it removed, and doesn't give me all the details for every single step. But I'm going to change this for this run through to include details of each step so that I can show you what it looks like and how it's performing each step and how it's making its decisions. I'm going to go ahead and also change my alpha to 0.20 instead of 0.10. What this is going to do is it's going to use that alpha for the cutoff of when it should be deciding something is significant or insignificant and deciding whether or not to remove that variable from your list of predictors. All right, let's go ahead and hit OK. And then we're going to hit OK again, and it's going to produce a model for me. All right. So notice this changed to like super long now. It always produces the final option at the bottom. So this is the final regression equation it came up with, and I copied that over here. Along with the model summary, there's the R squared adjusted value and the S value, and there's the model it came up with. Sorry. But I'm going to keep scrolling up further because the other thing this is going to report for you is, oh my gosh, here's all the steps. So if you keep scrolling up to where we used to be, there's step 1. So at step 1, it looked at all these p-values and it eliminated somebody. Who did they eliminate? Well, who's not present in step 2? It eliminated exactly who we thought it was going to eliminate, and that's potassium. And if we scroll over a little bit, which for some reason it's not letting me do, so let's try this. Nope, not gonna happen. Okay. Then you look at step 2 and you're like, oh my gosh, who's the highest now? Magnesium. Oh, that's probably who's going to be eliminated, and he doesn't show up in step 3. So it goes through and it just keeps eliminating for you until it gets down to stuff that is all significant. And I believe it did 10 steps, so let me go over and see if I can get it to show step 10. All right, and at step 10, here's who we have left. Whoever this is and these guys. And if you look at all their p-values, they're within the range I gave it of 0.2. So if you wanted it to be a little bit more selective about what's significant, you would change that alpha to not include things like, oh, well, that one's pretty close to 0.2. You know, maybe I would want to eliminate that. So there's a certain amount of automation that's happening here, but it's in the end, it's up to you. But the other thing you should look at while you're doing this is the R squared adjusted value and S. So as you look at S, remember we want S to get smaller and we want R squared adjusted to get larger. So as you look at these last, what is it, 4 that it's got here, it's still doing that, but just barely as it hits step 9. So if you look at the R squared adjusted value and the S value, it's still reducing S and making it smaller, and R squared is going up, but it's not going up by a whole lot. So that makes it a little bit questionable as to whether or not it is a perfect model. The last thing you should be looking at is the Mallows cup, or the Mallows CP. I always call it the wrong name, I'm sorry. And ideally, a good model should have the Mallows CP be close to the number of variables that it's using. And if we look at step 9 versus step 10, and this is where I really got a little upset with this model, is that the Mallows CP for step... sorry. Let's go all the way back over. Step 10 is pretty small, much smaller than its number of variables, so you have a high chance of getting something a little bit weird in there. And then I'm going to scroll down a little bit, and if you look at the variables it selected for that model, there's a couple things in here that are probably causing that, like the fact that we have 2 variables that are definitely looking collinear, and that's, you know, MO with a 13 and PB, aka lead, with a something almost at 15. So these 2 you probably should eliminate just from that. So that's something also to keep in mind when you're using the best subsets model. It's only looking at p-value to make its decisions. It's not looking at VIF or anything else to possibly choose things. So just to keep that in mind. Lastly, the model always produces for you anything with an incredibly large residual, including standard residuals. So these are possible influencing values, and that's observation number 12 and number 13, or sorry, 14. Alrighty, so real quickly, using this model that we have so far, so if we were just going to use this model to check, we should, last but not leastly, check our final conditions, so equal spread and the nearly normal condition. So I'm looking at part 4 right now of part 6. Number 4 of part 6. That sounds better. All right. So I want to do some graphs of my residuals. So I'm going to need to produce that for this model specifically. So in order to do that, we got to go back to stat regression. And then if you want, there's a couple different ways to do this. So I'm going to hit fit regression model again. And I'm just going to have it go ahead and use the predictors that we decided on from our previous one. So CD, MO, CU, or see you later, copper, BA, which I really don't think should be a part of this because it looks, oh no wait, it was B that was nonlinear looking. SR, PB, cadmium, and then K, which is potassium. All right, so once we have the variables we're going to be using in there, I'm going to make sure I click on this stepwise button and deselect this and use no method because I just want to look at the residuals for this model that it produced for us. Go ahead and hit OK. And then I'm going to go and hit graph and ask it to produce for me some residuals. So I'm going to change this to standardized residuals. And then I want the ones to check equal spread and nearly normal. So I want the histogram of residuals and the normal probability plot of residuals. I really don't need the rest of these. These are for checking nearly normal. I really do need versus fits, so I can check equal spread. Let's go ahead and hit OK. And hit OK again. So I don't care what it's doing right now with the other stuff, but this is what I want to look at. So the histogram looks kind of hard to read. This kind of looks like it might be normal. It kind of looks like it's unimodal. It doesn't really look symmetric. I hate reading the histogram a lot of these times, so I'm going to go ahead and shrink this and take a look at the normal probability plot. This is the plot you should be using to decide whether or not it looks normal. And if it looks like every single dot is on the straight line, then that's a good indicator that you have met the nearly normal condition. And it looks like I have a couple places, you know, right up here where it's a little bit offline, and it definitely curves away from center below 5%. So it's got some places where it doesn't look so normal, but again, we only need near normality for this to work. So I'm going to say, as you look at this, below 5%, sorry, this is the 5th percentile, I should say this properly. Below the 5th percentile, it appears to have some non-normal parts, but the rest is okay. This model fits the nearly normal condition. Okay. Next up, let's take a look at equal spread, which is the only other graph I haven't gotten rid of yet. Woohoo! All right. Let's see. Oh, it almost looks like it has an outlier up over here. That's a little concerning. But other than that, this looks good. It looks fairly spread out. It looks fairly random. Doesn't look like it has any patterns. There's no fanning. It looks good. So the nearly normal looks great, actually. So this is a pretty good model, I would say. So how do I want to say this? No narrowings or widenings or patterns. This looks equally spread. So pretty good when it comes to the condition analysis. So that's the only good news. Other than the fact that your large VIF values for a couple of your variables look like this has some collinearity issues. So I would actually handle that next if I was going to continue to use this model for something. So for that, I would actually probably eliminate the larger of the two. So I would probably get rid of the lead guy just because he has large VIF and the larger p-value, and see if that improved the model. It might remove some of the collinearity present and then you'll be fine. The rest of these are fairly small, so they're probably okay. I mean, clearly BA and SR, or barium and strontium, have some relationship with each other because they're pretty close to each other in value, but other than that, this looks pretty good. Remember, close to 1 is good. All right, now let's take a look at the other way to do this. So the other option on how you can do a sort of automated model is to look at the best subsets model. Look at the best subsets model. So we're going to go up to stat, regression, regression, and then best subsets. Yay! So here I want to use as my response the aroma, Next up, you have the option between selecting free predictors and predictors that are in all models. The ones that you want to make sure you include, you'd put down here. So anything you think was definitely going to be present or definitely want to be present, you'd place down here. I'm going to just select everything as a free predictor and then let it select who's going to be in there and who's going to not. So next thing you want to hit options. Given the option, you should always hit option. Okay. So next we have the minimum and maximum. I'm not going to mess with those. I'm going to ask it to predict 3 models here. So what it's going to do is going to give me, it's going to go through all the possible subsets it can. So there's 17 variables present. The example I give in here is, okay, let's suppose you set this to being 4. If you want to do models made up of just 3 variables from the 17 you have present, there's 680 options there. That's just for 3. It's going to go through all the ones for size 4, size 2, size 1, size 5, size 6, all the way up through 17, where it's using all of them. So there's a lot of things for it to check. So I really don't want to look at all of that output. So by putting a 3 here, I'm making it give me the best 3 for every size. So it's going to give me all the best size 1s, the best size 2s, the best size 3s, the best size 4s, yada, 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 so on and so forth. And then I'm just going to hit OK and hit OK again. And then it's going to always give you this warning because sometimes if you're dealing with a large data set with a large number of variables, this will take a longer time to run, like maybe all day. So just be warned of that. So that's why you want to go through the steps to eliminate anybody who looks nonlinear or has some questionable outliers first and get rid of those values before you run this option. Let's go ahead and hit yes. Woohoo! Luckily my computer's not slow. All right. So I just want to point out to you what it's doing, so I'm going to go up to the top here. So here's your top 1 variable guys, here's your top 2 variable guys, here's your top 3 variable guys, and so on and so forth. And then it gives you the R squared. We're going to ignore that because that's the one that's inflated. We're going to be looking at R squared adjusted, and then the Mallows cup and S to decide who's the best. The last thing it does is it produces this little table here with X's. So I'm going to move this over just a little bit. And then the X's here are really just like which variables got used in making this model. So once we decide who's the best, we'll use that to decide which variables we're going to be including. So if you scroll down, we're looking for, first of all, when I'm looking for this, what I look for first is, hey, who seems to have the best R squared value? And don't make the mistake of thinking, oh, well, it's going to be the last guy. I'm sorry, R squared adjusted. Oh, look, he's like not so great as even the one above him. Notice there's only one model size 17 because that's just throw everybody in there. In fact, if you scroll up, it looks like the, 12 to even all the way down to 6 range are better. So that's what we're going to look at. We're going to look at this range of values and try to decide from this list who's going to be the best. So I'm just trying to copy this over to Word. No, I don't want enumeration. Oh, that looks terrible. Let's not do that. I thought I had a good plan. It did not go well. No, undo that. Okay, sorry. Let me try pasting this one more time with gusto. No. That one's almost legible. It's horrible. I don't know why I'm trying this. It looks bad. Never mind. Okay, so here we go. So again, we're not looking at R squared, we're looking at R squared adjusted. So this second column looks pretty good. All right, this range of stuff. Then next you want to take a look at the Mallows CP. So we want this to be close to the number of variables that we have present, which nobody really does that all that well except for the stuff in the 15s. So those are pretty good. And the other thing we want to look for is the smallest S we can muster. So in looking at those 3 combinations, so I want to have a large R squared adjusted. So something up here I'm thinking. A larger or closer to the number of variables present, Mallows CP. Nobody really does all that well. And then last but not least, a small s. So if I was picking here, as far as who I think is the best, let's see. Oh, that one's pretty small, and my Mallows is not so horrible for that one. The second you go down further, your Mallows gets better, but then your S gets worse. So it's a matter of, do I want to be accurate or picking the right number of variables? This is a hard decision to make. And then you also want to have it be a good number of predictors, so you want this percentage to be high. And this would have been better if I would have gotten rid of some of my bad variables first. So I mean, I actually kind of like this number 10 out of all of them. I feel like it does a pretty good job. Its S is a little bit smaller, and this is where the art comes into this, a little bit more than the science. Its S is fairly small. It has a closer mallow CP, but even then, still, I would be worried about this. And again, what I would do next is I would run through this model with these predictors that it's selected here with the X's, and then ask it to tell me what the model looks like. So it would produce the analysis, and then I would remove anybody who has a high VIF. And I bet you once you remove the 5 VIF values, this gets, sorry, variation of inflation fracture, this gets even better. So there's best subsets. I like best subsets because it gives you more options as to who you could be picking that does a good job for predicting your model. And that's about it. More options. So depending on who you are, you're probably going to like one of these more than the other. There are people who think one of these is better, but to each their own. Alrighty, so that's how you can use Minitab to do an automated model and select the number of variables or which variables you should be using for a large data set with a large number of predictors.